So far, we've had variables and the state of the information that we need to remember to be able to like evaluate a program is something we've called a state, which is a function that maps variables to integers. But that's not really how it works on the computers that we're used to using. The variable points to a memory location, and then the store is a sequence of, well, bytes. I mean, we're going to store integers, so we still have some abstraction at this level, but a variable, we use an environment function to map a variable name to its location in memory. And then we use the store or the memory. We can use a location or an address to look up the values stored in that location in memory. So we've got one level of indirection now, which is kind of like the standard one that you deal with. I mean, in some way, this could be like the difficult point of moving from like Java, where you almost never really see a pointer, to C++, where all of a sudden pointers become, that is the model that you're working with. They try to hide it below a level of abstraction in Java as much as they can. So we've got these two maps anyway in this model. And we call one of them the environment, and it maps a variable to a location. And the other one is a store, and the store is essentially, you can think of it as like an array indexed by location values. So this is kind of standard terminology that when you take some language construct and let's say, oh, well, programs, statements are going to become procedures. And then once you have, and then variables, now we're going to have to actually allocate locations in the store and initialize them whenever we allocate a space for a new variable. And so declaring a variable will actually change the store by essentially allocating a new location in the store and then initializing that with whatever the initial value is. And then so the environment then points to the new location. So one of the things that I think he kind of did wrong in the book that makes it really a lot more complicated is he kind of embedded this next idea into the environment and not into the store. I'm pretty sure that's what he did. So I kind of changed it, and I put the next location into value into the store, because it's going to turn out if we do other things like right now, all we're doing is we're saying, oh, okay, we're going to set up this new abstraction model for variables. But, where variable refers to a memory location. And then the memory location has a value stored in it. And so that's more consistent. I don't know. So I don't know. Are there any questions about this? One thing we were able to do is if you remember function composition in Haskell, f dot g, and it's defined like this, you can, or like this, but you can say f dot g applied to x is f applied to g applied to x. So you might remember that, you know, I don't know, how can I get there is a way to get the chat up. I don't know. Is anyone saying anything in the chat? I feel like there's a way from.
If you want, we can tell you when someone puts something in the chat.
I don't know how it is for the host, but all I have to do is just hit the chat button on the bottom and it does like a pop-out window.
If you're talking, I don't think we can hear you.
Yeah, I think you're muted.
Okay. Is that better?
Yeah.
Okay. So here's function composition. And the idea is, you know, if I have a function from A to B and then a function from B to C, then I flip their names around and I get f dot g is the function that goes directly from A to C. So this means to look up the value in a store, I want to, so if I apply the environment function first, and so it's kind of like good to think of these as functions, although we might model them as lists of pairs. But the environment is a function that takes you from the name to a location, and then the store is a function that takes you from a location to an integer value. And so when you compose store.environment, you have a function to directly access the value like we had in the original state function. Now, I guess here, you know, I wrote these notes last year for and when COVID hit, and I was teaching this class, so I have a little bit more material to work with now. But so if we use maps, Haskell maps are kind of a convenient data structure for that behave a little bit like a function, but you can do things like tell me all the elements that are in the domain, or map over all the elements in the domain, or there's lots of operations that you can do on maps that are kind of nice. So, but the point here is that, oh, I'm saying NB, sometimes you see this in a text. It's like a abbreviation for the Latin phrase nota bene, which means important point to take notice of. So we're going to need a new environment for each kind of phrase we want to name. So right now, we're naming memory locations. And so env is the variable environment. And so you can think of it as the meaning of a variable is a location. And that's what the environment is, a data structure. So this is a kind of a, I think, like a nice, like a good thing to try to way to think about this is that, oh, let me try to get my Wacom pad going. Where is it? Oh, don't tell me it's in the other room. I'll be right back. Okay, I'm back. So you could think of, it's like a really good idea. Like whenever we have these mathematical things, we say, oh, it sounds complicated. Okay, a state is a function from variable names to values. Oh gosh, functions, that's like a complicated thing. But what you want to do is for the code side, what you can think of is you can think of that there's two things we need to remember. And the environment is a way of remembering the meaning of a variable name. So the environment, oh, that's not turning out too good. I should say it is a data structure. ENV, can you read that? It's a data structure. Come on, what's wrong with this? You know what, I wonder if my nib is worn out. Like, I don't know why they would make it so that that happens, but
It's all more.
I bought extra nibs in case this happened. Could that be what's going on here? So anyway, an environment is a data structure to remember the meaning, and a the memory is, just a data structure to remember what's stored in each location. So you can think of these things as data structures instead of, mathematical structures like functions. When I was a younger programmer, I always, like if, I don't know if you will have, but like for a quick and dirty go-to data structure for me always was lists. Like it's easy to do things with lists. Let's see if this works any better. No. I can't do this, huh? This is terrible. All right. Well, maybe on the whiteboard I can do it better, but and it wasn't the nib. So now what we were going to do though is variables are just one kind of thing. We're going to have procedures, and all the procedure name is going to be the environment for procedures maps a procedure name, which is just going to be a string, to a pair, which is the statement that is the body of the procedure, together with the environment that was encountered at the time that the procedure was declared. And the reason that you need to keep that environment is you need to keep that to make sure you don't call things that weren't declared before the procedure was declared. And that prevents some, unpleasant kinds of behaviors. So it turns out in the other book that, that we're not using anymore. He had this great, this is chapter 2 of the other book. And in the, and it's each chapter in his book was named after kind of like the new feature that's being added to the programming language. And what we're adding now is the ability to abstract, which means to bind a name to the structures that we have in the programming language. Okay. So we're going to want to do it to other things. What are the other things that we have? Well, we have arithmetic expressions, and arithmetic expressions would correspond, binding a name to that would be like a function of no arguments. Binding a name to a piece of code, to a statement, is a way to kind of compact your code in a significant way. And so that's binding a name to a statement is typically what you would call a procedure. Some languages make a distinction between functions and procedures, where procedure is a name bound to a program that can change the state of memory, whereas a function, our arithmetic expressions had no operators in them that could update memory in any way. All you could do is look up the value in memory. You can refer to a variable name, but you couldn't modify a variable name. So I don't know. And so let's see. Let me try and. How's my audio? Is it terrible?
You sound good.
No, it's
Okay.
coming through fine for me.
Okay, good. I'm just trying to see if I can share. Let me see if my Wacom thing works any better on the whiteboard. I think I'm on the whiteboard now. Yeah. So remember we had a expression, and it was either a variable or it was I don't know. He didn't call these C's. C is an int. He called those V's. And okay, he labeled those X's. Let's see. Let me make it consistent with what Huddle did. So X, and then he called this a V. And then we had like A1 op A2, where so this is V is an X is a var, and A1 and A2 are previously constructed A expressions. And op, what do we have is times, plus, times, and minus. So, and then do we have a not also? Oh no, not in A expressions. In the book, he separated A expressions and B expressions. And that was a way to actually avoid kind of like doing what I asked you to do on the homework, which is what you have to do if you're going to remain untyped, or you're going to have to build a little type system to type check, and then you could keep those things separate. You don't have to interpret expressions that could be Boolean as integers. Okay, so we've got something like this. And so then we could also say, you know, or it's a F, or F is an element of fun name, which are just going to be strings. And so this would, and I guess I got to say F equals, let's say, A1. So here's a way to add functions, add a way of binding a name to an A expression. And you could do the same thing for B expressions. You could bind a name to it. And so now you could say stuff like, oh, I guess we got to do something like this, though. This has really got to go someplace else. This is a declaration. And we have to make this in the other language if we want to call it here. One way to do it, though, in an expression language is to say let F equals A1 in A2. So this doesn't actually go here if we want to do it that way, but this one is like a local binding. This binds F to A1, and then when you evaluate A2, whenever you see an F, you evaluate A1. So this would be binding names in A expressions where we add it as a construct to A expression. Okay, so let's go back and look at oh, come on. Participants 125. I'm trying to go back to the notes, but I can't seem to get there.
Do you know where about in the book we are right now? So I can kind of follow
This
along with the
is
lecture.
chapter 6 on page 78 through, starting on page 78. God, I don't know. I'm like, how do I get rid of this? All right, let me try turning that off. I can't get the little bar which says stop share. Are you still seeing my whiteboard? Aha.
Yes. Yeah.
Okay. And now do you see my screen? Not yet.
At the top, it's supposed to note the lecture 12, adding abstractions, variables, procedures.
Yes. Okay, so you're there. Good. All right. So then we need a little notation for dealing with these things. And I guess, let me look here. Now you could, like I said here, up above, that you could map. So one thing we can do is we can make a single environment that is a record. It's a data type, and the constructor for this is env, and then what you have inside are record fields, env and envv and envp. And so then it saves a lot, because each time we want to name a new thing, we have to add a new environment. And so if you start passing all the environments around, you end up having a whole bunch of arguments. Now, sometimes it's the case that, like, for example, to evaluate an A expression, you only need the environment for variables. You don't need the procedure environment, because there's no way to refer to a procedure from an A expression. But there is a way to, but if you package it together, you're passing along extra information. It's a trade-off between readability, really, and kind of compactness in what data structures you're passing around. So now then, this is a question like, do we want it to just be a statement that we bind to the string, or do we need to save the environment, which would be this whole thing, right? And what does he do? I'm trying to remember here. There's envp would be his environment. He doesn't get to that until page 85. All right, it's not until later that we have to worry about adding that, but I was adding it in the notes at this point. So we don't need to worry about the environment in the environment for procedures at first, but later. So you can think of these environments as, being maps from names to syntactic classes. And every time you add a new syntactic class, that's the thing I loved about Schmidt's book, is he had these mottos, and his motto was every semantically meaningful syntactic class can be named. So you can bind names to any meaningful syntactic class. And what you're going to see in a minute is we're going to have to add declarations, which is a new one. And if you name declarations, you get something like a module structure, which is pretty interesting. So anyway, here I'm basically saying, look, in the notation, I'm not going to worry about, I'm just going to call the env, lowercase env is something of type upper env, but remember it has these multiple parts in it. And even though this should be something like env dot envv, update that one, or update envp here, I'm just going to assume that there's no confusion about this. The code has to implement every detail of that, right? But for the notation, it just makes it much more readable to assume that if you know X is a variable name, that this means update the portion of the up here. Oops. Man, things are just behaving so weirdly. Okay, where did I go? Yeah. So this notation, oh, don't jump. This notation means update this field. And this notation, which looks identical, except the type of this thing is a procedure name, means update this field of the record. There's an insert function in that maps can deal with. And so here's the actual Haskell code for like updating envv. You say, okay, env, and then the field envv gets the value, insert x, there's your x, at loci in the current envv. So this is a little bit circular seeming, but you're taking the current one and you're updating, you're taking the current variable environment and adding something new to it. And you can do the same thing for envps. Does anyone have a question? So there's a map.insert function. And here is how you would encode this particular informal notation would get encoded in Haskell like this. Now, yeah, here's some more map notation. So we'd like to do something like, this, which means but we want to really apply the environment. So we'd like to say, well, get ENVV from and look up X. But to look up the value of X, so this is like in case you haven't really used records in Haskell before. I'm up here to look up the value of X in ENVV or Q in ENVP. We write the following, where E is an environment. Then in Haskell, I think they just added the feature to write E.envv, but in Haskell, the default is that the field names are functions that take an environment and return whatever's stored in that field. So this means look up the variable environment in the environment E, and then there's a bang operator, which is essentially takes a map and an input and returns a B. So here's my map. Trying to scroll down just a little bit. If we could go see that record field again. Here's my ENVV map. And so I apply ENVV to E, which is some environment. And then I look up X. Or I can get the procedure part of the environment by applying ENVP to E. And excuse me, the bang notation means like apply this map to that argument. Any questions? Now, and when you're reading the book, you're going to see that we are doing, in this presentation, I presented a little bit differently just because his presentation isn't quite as clean as the one where we do something different. So like I said before, and if you look in his presentation, like at the bottom of page 84, for example, can you see page 84 at the bottom? He's got this var declaration construct. So we're adding a new thing. We're going to add a new thing. And if you look at the line above, like at the, he's basically saying, okay, look, you're going to declare a new variable X on the bottom of the bottom condition is. And maybe, I don't know, is there anyone that doesn't have their book? Maybe I can just, I don't know if I can write it out here or not. Maybe not. This is so strange. I just don't understand what's going on here. Like for me, first of all, the menu is like double the size it normally is. So there's some kind of monitor mess up going, and I can't move it. can you still see the thing I was showing you with stores with the orange line on it?
Yes.
Okay. Okay. So what he ends up doing is he ends up manipulating the next location variable in the, he keeps it as a value that's in the environment for variables. But the problem is that you're going to need the you're going to need the next location when you're using other, like if we add records, for example, we need access to it. So it makes more sense to keep the store, let the store keep track of where the next location is that's available. So the store is kind of growing like a stack as we you know, we enter a new block. It's going to grow with local. We're not talking about blocks yet, but you know, we're going to have blocks are going to be a kind of abstraction. And so it's going to grow. And then as you exit the block, the variables that were declared local to that block disappear. And then, you know, as you enter a procedure, it's possible that it has some local variables that it allocates. And so when you call the procedure, you want to allocate those variables. When you exit the procedure body, you want to get rid of those variables. So memory is going to grow at like a stack. And so that means also that for debugging, I've found that it's useful to remember what was the biggest size that the memory ever got to be, because the values there will still be stored in there. So even after we, you know, essentially free space, all we do to free space is we just move this pointer next look somewhere back in memory and just reallocate over the top of what we previously did. Does that make sense? So he's got a variable, a dedicated variable in the environment called next. And I called it next loc. And so I say a store is a map from locations, and I just take locations to be integers, to integers. So this is a store just maps a location to integers. And then since we never expect there to be negative store, you know, you never address memory into the negative space, we reserve the location -1 and -2 in the store to keep track of the next location that's available in the store. And -2 keeps track of what was the biggest the store ever got to be. So this is what we want to initialize those to be. Okay, so now how do we make an empty store? Well, there's a function for building maps where you specify a list where this is the input value and this is the output value. And this is the input value, and this is the output value. So you specify this list, and you can say from list. And so S0 will be a store that will have in -1 will get mapped to 0. Max store size -2 will get mapped to 0 also, because nothing has been allocated yet. So the empty store, we got to set next location to be 0, because that's where we want memory to start. And we got to set maximum store size to 0, but everything else is undefined. Like if you try to look up any other memory locations inside of S0, you're going to get an error. So here's how the allocation function works. Alloc takes a store and it returns the address of a new location that has been allocated together with a store. So, which is the new store that's been extended. So alloc, if I want to alloc from a store S, what I get back is a pair L, which is a location, and an S prime. And what is L? L is take the store that you started with and look up the next location. And in the first, from the empty store, that would be 0. And then you update next loc to now be L plus 1. And now I've got an S double prime. This is a new store that has a new location and has been had next loc updated. And then to keep track of the max store size, we just say, okay, insert into max store size the maximum of L plus 1, or what we currently thought was the max store size. So we could have like grown memory really big at one point, and then it shrunk way back, and now we're working our way back up. So the maximum is still out here. So what I want to be able to do is when we're evaluating our semantics, we sometimes want to look at, well, it's going to turn out that actually a program allocates storage and then gets rid of all storage. And so there'd be nothing for you to look at whatsoever after you evaluated a program. Memory will be empty. So you can't use that very well for debugging. And so if we keep the max store size, the data that was stored in there, the last data that was stored in there is still in there. It can be confusing though, because at one time it could have been big and then it got small and then it filled up a few more and then it got small and so you never know sort of like you can analyze the program, the simple program you're trying to evaluate and see what's going on, but it can be confusing. So the thing about alloc, and the thing that I was trying to show you before on the rules on the bottom of page 84, is that he's actually kind of like taking care of this bookkeeping in the semantics of declaring a new variable. And alloc abstracts that away. So it's going to simplify the rules. Okay. Any questions? Really? Come on.
Could you go over like an example with values?
Not yet, because we don't have the ability to declare a new variable yet. So let's go a little bit further and then we can evaluate. Well, in fact, that's coming up right here. All this scribbling is going to be an evaluation, okay?
Okay.
So here's the new syntax. And it looks like X gets the, and this is different from his because he does something else that I find just preposterous, is that he makes a kind of declaration, which is a list of variable declarations. And then you're only allowed to declare procedures after you've declared all variables. I don't get it. So anyway, here's my version where you can interleave them. You can put together, you can declare a couple of variables, you declare a procedure, you could declare more variables. So anyway, so we still have the assignment, skip, semicolon, if then else, while. And now we have this thing that says begin, and you give a list of declarations, and then I don't know, probably that in should disappear. Begin, list of declarations, and then S, which is a statement. And then there's a way to, since a procedure P is a name bound to a statement, that means calling P is a kind of statement. And then the two things that we can declare so far are, we can declare a variable and we can give it an A expression, which is the initial value. And it has the keyword var in front of it. And then we have one that says proc P is, and then the body of the statement. This version's easier to parse. I have parser for this, so you can try out your programs and stuff. And there's just no reason to have this constraint that variable. In his, it says like decal P followed by decal var followed by, or decal V followed by decal, he uses DV and DP. So anyway, so here's a simple program in this new language. I don't know, can you see it? Even though it's scribbled on, I might have a different, this one here might show it better actually, if I can get it to scroll.
It's kind of hard to see on my screen. I guess it is. Yeah.
It's what? Is
It was
this one?
hard to, like before it was hard to see my screen.
Is this one okay though?
Yeah, that one's good.
It's easier to read, I think. But I just got to go over here and get this thing. There we go. Okay. So it says begin, and then we declare a variable X that gets initialized to 0, and then we declare a variable Y that gets initialized to 0. And see, in the syntax, I kind of cleverly put these semicolons after declarations. And so if the list of declarations is empty, then there's nothing to declare. So it could be better to get rid of that in, because if there are declarations, then what you're going to get to is a semicolon before the S. But anyway, here is, and maybe I can zoom out. I think you can almost see all of the syntax here. So then it declares a procedure P that says this variable X gets the value of this variable X plus 3. And then procedure Q says call P. So it just evaluates this. And so now we can say, okay, begin, here's our declarations. And then we say in, okay, now declare X to have the value 9. And now declare proc P to be X gets the value of X plus 1. And kind of the question is, if I call Q, which P should I be calling? Should I be calling this P that was locally declared, or should I be calling this P which was declared above? And yeah, which X should this refer to also? Presumably the X in P refers to this X, not to that X. So these are kind of the scoping rules. This is on page 88 of Huddle. Does anyone want to guess? I mean, what would you like to see? Do you want Q? When I call Q, Q just says call P. Do you want to call this P? Or do you want to call the P that was there when Q was declared?
So would X, the final value of X be 13?
Well, it depends on
Because it assigns it 9 and then it adds 1 and then it calls Q, which calls P again, which adds 3.
Well, that I'm not sure actually we can make that one happen, because you're kind of like mixing. First you want to actually call this P when you call Q, and declaring a procedure, this doesn't get evaluated. It only gets evaluated when you call the procedure, right? So this declaration does initialize X to 9, but calling a procedure or declaring a procedure, this is only evaluated when P is called. So this doesn't actually, if I just executed the code here, well, it's hard because the things are up there, but if I just executed like begin var X equals 9, proc P is X gets a value of X plus 1, and then X gets a value of X. X will have the value 9, because declaring a procedure does not evaluate the procedure at the same time it declares it. So what would people like to see? I mean, what do you think? I mean, come on, you all know programming language. Tell me a programming language and that you would use to look at this program and think about that programming language that you know, some declarative programming language, and figure out what gets bound to what.
To me, it would make sense that the P is overwritten with the X equals X plus 1, but in the book, that is not the case, it appears.
Well, so here we are. We're kind of like at a point where we're looking at some constructs, and something similar exists in your favorite programming language, and yet you're not quite sure what it should do. Like, what should this do in Java? Essentially the same program in Java. Well, and I don't know. Does anyone else have? So does anyone know what would Java do here? All right, let's see if I can't seem to make this pen work. I have no idea why. It's so strange. It's like, I don't know, my machine automatically updates with stuff, and I should really get rid of that feature. I thought, okay, going to Unix, it's probably safer in a lot of ways than running on Windows, which is a big target, and even Macs are kind of a big target. But Linux is not that big of a target because not that many people are running it. But when you start downloading packages, and you have to download to set up your environment, you have to download a lot of stuff. And I mean, it is just flying by on the screen, hundreds of lines of stuff that's getting downloaded. And depending on what package manager you're using, they are like verifying some kind of hash code that was produced when the software was created to make sure you're actually getting that version of it. But not all of it is like that. So who knows what happened to my poor computer, but let me see if I can make this pen work a little bit. Oh, I don't know. I can't even get to it anymore. What happens if I do that? Okay. All right, at least I could go to the whiteboard, but how am I going to remember the program? Oh, it's in the book. Can you see the whiteboard?
No.
No?
No.
Hmm.
Yeah. Yes.
Okay.
Yeah,
It
that's
took a minute to load.
Okay, good. And can you still see the program or not? Over to the left? Probably not.
No, just the whiteboard.
Okay. All right. So it's like, okay, begin for X gets the value of 0. So has anyone heard of dynamic and static scoping?
Is it anywhere similar to like dynamic and static programming, or?
Well, there's two, yeah, it's related, right? There's scoping and then there's typing. Now, we're almost out of time. It's generally the case that the variables that are in scope are the ones that were in place at the time that a declaration was made. So, and that's true in virtually, unless you're programming Well, even Perl, I think they changed the default. The default was originally dynamic, and it gets too confusing. It's basically, it's kind of like if you don't know anything about implementing programming languages and you implement a programming language, you'll probably implement dynamic scoping. But it's generally considered to be an error. Although there are some neat tricks that you can do it with it. And in fact, I think I always knew that there was something called Jensen's device that was invented by a Dane that uses it. But in any case, let's look at like what does memory look like at each point here, right? So we start out with the empty memory, and then we have one location that has a 0 in it, and X refers to that, right? So maybe I'll write it like this. We're going to run out of time if I don't just get going. So I'll write it like this. We have memory, we have an environment where X points to location 0, and the value in location 0 is 0. And then, okay, so maybe I should do, this is the environment, and this is the store. So it's still empty. And then here, there's one location with 0. So X points to location 0, and stored in location 0 is a 0. All right, is this notation making sense? I'm not hearing anything. Uh-oh.
Yeah.
Okay. I'll make it a pair though, so that you don't think, oh, there's something different between here. So this is the store, and this is the environment. And so X points, and then after I go here, I get, Y points to the next location, which is 1, and I get 0 gets mapped to 0. And now location 1 gets, maybe I should make this like a 2. Location 1 gets mapped to 2. And then we add into our environment P. Oh, I apologize. I need to keep X in the environment also. I need to say Y1 comma X0. Oh, that was good. Where did that come from? I was able to change my line width. Okay. And then we have like P points to this, and this environment. So P is a pair, the environment. So this is ENVV, and ENVP is empty. And then after this line, ENVP says, okay, P gets mapped to 2 things. X gets the value of X plus 3, which is the statement, and I'll call this E1 and E1. And here, Q, then it gets extended so that Q gets a value, gets bound to call P, and really this is like, the ENVV, this one, and the ENVP. So Q can know about P because it's got the it's got an environment there. So now when I come down here, that means that P in this environment, when it looks up X, it gets location 0. Now down here, I keep going with ENVV. So ENVV is equal to this one, plus now I get that X gets the value of 9, and I still have that, I'm sorry, this is a new X, and I got to allocate memory for it, and the next location is 2. So X is paired with 2. Oh, come on. And memory location 2 has value 9. So this is the store, this is the environment, and now I update this thing, and so this one has, the P in it also. And then, so if this is, the ENVP part, now I update that so that in my new ENVP, I get an entry for P, which gets paired with X gets the value of X plus 1. Oh, God. And this one, ENVV1. And so now this, and then behind here is the Q pair and the old P pair. And so what this means is that this X, when I am looking to evaluate this X, I'm going to look in this environment, and it says X points to location 2. And this X also points to location 2. It's the most recent one. And then remember over here, location 2 has the value 9. Right? And so when I call Q here, what do? I go down in here and I look up Q, and the entry for Q has the environment. When it tries to figure out what does call P mean, what does this expression mean, it uses the previously declared one, and so it gets that X gets the value of X plus 3. So this Q then is still a call P, but it refers to this P. And when you call this one, it knows about X being the location 0. So this X, so if I look at memory at this point, I've got what? X is going to 2. Y is going to 1. This is not memory, this is the environment. And X goes to 0. And so this is the one that we find. And then location 0 still has a 0 in it. So but this X is that one. So what we're going to do is we're going to call Q, which calls P, which is going to update location 0. So our memory is going to look like 0, 0, 0, 1. Is that right? No, I'm sorry. 1, 2. And then we still have a 2 is a 9. And so when we're done with this program, it's going to call this P. This P's X's are referring to this X. And so this becomes 3. Maybe I'll write in red now or something. This one becomes 3 because of the call to Q. And then Y gets the value of X. And so Y is this variable that was equal to 2, but now it becomes 9. And now when we exit this, we actually get rid of, this goes away, and this goes away. And we end up with, but then when we hit this end, we also deallocate those. So in the end, memory is empty. So this is what I was talking about. So the maximum, if we printed out the maximum memory that we had after this program was done, we'd see that X is bound to 0, and 0 has, location 0 has the value 3 in it. Y is bound to 1, and location 1 has the value 9 in it. Oh boy, I apologize. I really went over. Well, is anyone still there?
Yeah.
20 people. Okay. Questions? So the rule is that if you read code and you down here, let's say this was way far away in your code and you read this Q, and maybe this is closer, but suppose this P was hidden way up above. You'd say like, oh, Q calls P. Oh, there's P. And so you want to be able to read the code, and at the time that you're reading the code, figure out which bindings are in place. And that's why we end up saving the environment when we store procedures, so that it knows what's P bound to. Oh, P is bound to this, not to this. Now, you can just save a stack, and this is why it's kind of like the naive thing to do, or the thing that you end up doing kind of by default. If you kind of write naively a compiler or whatever, an evaluator for a programming language, you end up implementing dynamic scoping, because what all you do is you just keep pushing things on. And when you see call P, the last thing on your list was, at that time, was, oh, P is equal to X plus 1, even though Q was defined up here. And at that time, the only P that was in scope for the definition of Q was this one. And so that's why we have to carry around the environment. And it's basically considered an error. Lisp, the first version of Lisp had this problem. So it's not that uncommon.
If we had redefined the procedure in the second block, it would have called that one instead.
Yes,
Like if we redefined Q.
If you had redefined Q down here and it still said call P, it would call this one, because the one that's in scope, when you would see that, you know, instead of just call P, it said proc Q is call P. The thing that would be in scope, the nearest thing named P would be the last one, would be this one. Good point. Good question. All right. Well, I can't seem to get out of here or figure out how to exit screen sharing. I just don't understand this stupid little menu gets stuck. So anyway, I'll see you on Thursday.
Bye.
Thank you.
See ya.